I'll be running through the tutorial. I'm here on Windows, so you can see down here I've got my Windows stuff running. So we got the tutorial here. I'm going to be talking about the tutorial, and I'm going to be going through pretty much everything in the tutorial. Let's start at step 1. So, by the way, I'm going to be running this, as I said, on Windows, and I'm entirely inside of WSL, which is the Windows subsystem for Linux, where you can run a Linux virtual machine that connects to your Windows computer. If you're also in Windows, then you can look at the guide to using Reach on Windows, and it will talk about enabling WSL, installing Docker, and you can set up VS Code to connect to your WSL instance. But I don't use VS Code, so I'm just directly using a terminal. We make sure that we're ready to go to make sure that we make sure we have make installed, which is pretty standard on Linuxes. We have to have Docker installed, and we have to have Docker Compose installed. So once we know that those are all there, what I'm going to do is I'm going to make a Reach directory in my home directory, and then I'm going to make a directory for the tutorial. And we got the tutorial right here. Then what I'm going to do is I'm going to install Reach. And we install Reach by basically downloading it from our GitHub repository. So now we've got Reach installed here. And we can check to make sure it's working by running Reach version. So we're in version 0.1. And we can download the images by running Reach update, which is going to pull... first it pulls the Reach compiler, then it pulls the Ethereum devnet, then it will pull the Algorand devnet, and then it will pull what we call the runner, which is basically a JavaScript support library for running test instances of our tutorial, well, really of any Reach program. So that's what it's downloading right now. I really love Docker. It's pretty amazing because you don't have to worry about exactly what version of everything you have installed, which is such a pain in the neck. I remember when I was a little kid, and I went to my first Linux user group meeting in New Hampshire, and how it worked is you would go, and then you got someone would hand you a CD with Linux installed on it, and then you could go home and install it because the internet connections weren't fast enough to actually download it well. Alright, so we now got Reach installed, and we can verify that it's running properly by running Reach compile, and we can run and get the help message. And that just says that, we really ran the Reach compiler. Now, this Reach compiler right here, behind the scenes, it starts up a Docker image that runs Reach compiler, and then that's how we get to it. So, we've now totally installed Reach, and we are ready to go. If you're doing this at home, I highly recommend heading over to our IDE and text editor support. Right now, there's an IDE that's very well supported for VS Code. We also have walkthroughs for how to use it in Atom and Sublime. I'm going to be using NeoVim, and you could have NeoVim talk to the VS Code IDE language server protocol, but I don't do that. I just configure it to be JavaScript, and then get going from there. Alright, so now we'll switch to the second chapter of the tutorial. And the idea of this chapter is to just walk through some of the basic points about writing a Reach program. So what I'm going to do is I'm going to edit a file called index.rsh. So RSH is the extension that we use for Reach programs. You can help remember that by remembering that our website is reach.sh, so RSH. And Reach files are a subscript of JavaScript. The whole language is a subscript of JavaScript. So when you're writing a Reach program, you are writing something that is syntactically JavaScript. By the way, feel free to ask questions at any point. I'm happy to elaborate on anything. You can type questions into the chat, and I'm not watching the chat, but Michael is, and he'll pull that out. Or you can just unmute yourself and just ask a question, just normally with your mouth. That's totally fine. But if you don't want to use your voice, that's fine. You can type it, and then Michael will ask for you, and we can talk about anything. So anyways, so as I was saying, that when you write a reach program, you're writing a subscript of JavaScript. And so it's easy to configure your text editor to just treat reach programs as JavaScript if you don't want to install one of the extensions. That's what I have in my NeoVim. Now let's write this first program. So we start off by including a string at the top of the program that says this is a reach program. Basically, it's just kind of a way to help the compiler know that you intended this to be reach, not just some random JavaScript program. That version number right there will make it so that your program will be consistently compiled in future versions of reach. Now, one of the central concepts of reach is that when you write your program, you are describing an application. So you're like using JavaScript to describe an application. And this application is a value in your program. And that value, we typically name main. You can name it whatever you want, but main is what the compiler knows to look for if you don't say anything. Just like, when you write a C program, it looks for main, or a Java program, or Python, just a common name. So we'll define a reach application. And reach is a function that takes 3 arguments. And these arguments, each one of them has a particular purpose. So the first argument are options for compilation. By the way, if you feel as though the size of the text on my screen is not big enough, again, make a note in the chat, and I can, or say something, and I can increase the size. We're not going to explore any of the compiler options during the tutorial, but there are a few that are available. The next one is the set of participants. The set of participants, and then there's the body of the application. Now, already, there's a point at which we can kind of talk about one of the big ideas of reach, which is this concept of a participant. So some programming language for building dApps, they focus on building the smart contract, which is one of the sort of exciting pieces of a dApp that is the thing that actually runs on the blockchain that manages the shared state of the program. Now, when you write a reach program, you never explicitly construct the smart contract. Instead, it is implicitly derived from the body of your program. Instead, what you do is you get to describe what the individual users of your program do as they're running through your application. Now, it's very common when you're describing protocols, cryptographic protocols and applications, to use prototypical users. And these users are commonly called Alice and Bob. I think there's a security authentication protocol paper from like the 1960s that first used these 2 names because they're, A and B, there's a woman and a man, so, it's kind of a nice set of names. So we tend to describe in the documentation protocols using Alice and Bob. Now, despite being personalized names, these names are not particular people. They're the role of Alice and the role of Bob. So as an analogy, suppose I were to describe to you the rules of the game of chess. I might say that white has 16 pieces, and black has 16 pieces, and white goes first. So there I'm using white and black to stand in for the roles of the 2 players of the game, and I describe things about each one, and I describe things about how the game works, where white goes first, and I might say white goes first, and then black goes, and then they take turns after that. So reach programs operate on a kind of a similar principle, where you describe who's playing the game, you know what I mean? And in this case, we're going to say that there's a participant whose name is Alice, and we can say specific things that Alice has or knows right here. We'll explore that later. This would be like saying that white has 16 pieces and black has 16 pieces. After I say that Alice is a participant, I'll also say that Bob is a participant. And I'm using strings here because these names are part of the external interface of this program, meaning that these names are externally visible. They're not extraneous details of this particular program. there's this general principle of programming where if I have a program, I could like change all the names in the program and the program would still mean the same thing. So if I were to talk about like, f of x equals x plus 1, that's the same thing as f of y equals y plus 1, even though I changed the names. So in Reach, when a name is actually meaningful, we always make it a string because that means it's string data that is exposed. So in this case, Alice and Bob will be exposed when the program gets compiled. Now, this array right here is where we write down all of the participants of the program, and then those get represented in the body of the program in variables. And I'm going to choose the variables A and B. Now, I could choose the variables Alice and Bob, but I'm specifically going to choose A and B to help emphasize the fact that this name has nothing to do with this name, because this name is the external specification, and this one is just the name that it will be used for in the program. Okay. Now, let's write inside here the body of our program, and we're going to write a really simple one. We're going to write that the program just immediately exits. So at this point, I have now written the sort of like smallest Reach program. I guess technically we could make one smaller because we could only have one participant, but we'll have it there be two. Now at this point, we can actually compile the program and something will happen in the program. So let's actually pop down to the terminal and just compile it real fast so you can see what I'm talking about. This is not exactly what the documentation, the tutorial says, but you're getting the raw experience by going through me. So we're going to compile the program, and it's going to say unexpected write token. Yes, why is there an unexpected write token? It's on line 15, which is right here. And why is that? That one matches. This one matches. Did I not save? Write paren token. It's wrong. Should I not have that there? Okay, so because I had this comma right there, I thought that there should be another argument to the function. So anyway, so I just compiled my program, and Reach did some really stupid verifications, which I will talk about in a much later part of the tutorial. And what happened other than doing the verification? Well, what happened is this new directory was created right here called build. So if we look at the build directory, we'll see that there's this new file in there called index.main.mjs. That file right there is the output of the Reach compiler. When it runs, it is going to produce for us the things that we need to run a dApp. Now, but what do we need to run a dApp? Well, every dApp essentially is made up of, let's say, 3 components. And I'm going to do some ASCII art right here. So your program is going to have the user, and then the user is going to interact with a front end. And then that front end is going to interact with the middleware, and that middleware is going to interact with your smart contract. Smart contract. And that smart contract, it exists. Let's get some more beautiful ASCII art. There's this little barrier right here. This barrier is where the blockchain is. And we call the blockchain the consensus network because blockchain is really a technology, and consensus network is a way to, it is like what the product is. So as an analogy, you can have a car, and then you can have an electric engine, or you can have a gas engine, or a steam-powered engine, or a leg-powered engine. So the product is the consensus network. So your smart contract runs on the consensus network, and it interacts with a middleware that knows how to sort of speak the SDK of your particular consensus network and knows the particular details of your smart contract. And then that is managed by a front end, which your user actually interacts with. So your user is, of course, a human, you know what I mean? So like this right here, this region is, this region over here is like the computer region. So only past this line are computers. And so like this area right here in the middle, this area is the user's computer. I have no delete key on my keyboard. I only have a backspace. And then finally, the last thing that I want to kind of indicate is what reach makes. And so what reach produces is this part right here. So reach produces these things. It produces for you the middleware, and it produces the smart contract. And your program, therefore, doesn't need, when I say your program, you're going to write a front end, and your front end is going to interact with this middleware, which has a well-specified interface specified by your reach program. And then it interacts with a smart contract that the reach compiler generates. And this connection between these is automatically managed by reach so that you don't need to worry about the particular low-level details about how the smart contract works or how the consensus network you've chosen works either. So in between these pieces right here, the middleware and the smart contract, that's what's in this index.main.mjs file. If we want, we could go look at that file and see what's in there. So it contains in it a function called Alice. And it's called Alice because you named your participant Alice. And it also has a function named Bob, right here, Bob. And it's named Bob because you chose the name Bob. So that's what I mean by the interface to the middleware is chosen by you in your reach program. So this right here is part of the reach program. But then in addition to the Alice and Bob functions, which are this middleware, it also contains the smart contract. It contains a version of the smart contract for Algorand, and it contains a version of the smart contract for Ethereum. On Ethereum, we just have the raw compiled form of the bytecode for the contract, whereas on Algorand, we actually contain the source code because the way that you interact with programs on Algorand is you typically upload your source code to your local Algorand node, which then compiles them and then gives you back the bytecode, which you then launch. That's just kind of a different way, sort of like the standard way those consensus networks work. So let's now write a really simple front-end program that just connects to this program, which of course does nothing, and then go from there. So I'm going to go make a new file called index.mjs. If you are familiar with JavaScript, you may be surprised at the extension MJS. The reason that we use the extension MJS is because we're producing node modules. So behind the scenes, when we are going to run our test programs, we're going to be using the node, the node JavaScript runtime. Okay, so now let's go edit that. So now this program is a normal JavaScript program, and we're going to import into it some stuff from the reach standard library. So first we're going to import the function loadStandardLib, and we're going to import it from the reach standard lib node package. This node package, by the way, it's just on node. So we can go to npm, and we can go look for, that's not what npm.org is, it's npmjs.com. And then we can go look for reach sh standard lib. I might need to put an at there. Yeah, there we go. So we're just getting this standard library right here. Okay, so we'll get that standard library, and then we're also going to import the compiled backend from the build directory, and it's named main.mjs, which, as we saw, we can just see that, right? It's build main.mjs. Okay, so we've imported those things, and now there's kind of a little bit of an annoyance with JavaScript, which is that many programs on JavaScript, in JavaScript, they block. What blocking means is that you do something, and then your program just stalls waiting for something to happen. So a good example of blocking behavior would be like contacting an external website. And so your program will just stop and do nothing. And there's this pattern that has emerged in JavaScript programs where the proper way to block is to return something called a promise. A promise basically is a value that in the future will contain another value inside of it, which is the one that you actually want. And it used to be that you would write very complicated promise chaining code, but nowadays in modern JavaScript, you can use the async await keywords of the program. And now this is where I get to kind of the unfortunate thing, which is that you can't use the await keyword at the top level of a program. It has to be inside of a function. So what we're going to do is we're going to write a function. Right here, we're going to write a function, and then we're going to immediately call that function. And because we're immediately calling the function, that basically means that inside of these braces is a piece of code where we can use await. And when you write async in front of the function definition, this right here is a function definition, that signals to the JavaScript compiler that this is one where we'd like to be able to use await. So now that we've done that, we can now actually grab the standard library, which requires an await. So we await the standard library. Because remember, we loaded the standard library, we got this loader, and now we're going to actually call it. Then what we'll do is we'll create test accounts for Alice and Bob, and we'll make it so that each one of those test accounts is going to start off with 10 units of currency. Now, as I mentioned, when Reach compiles your program, it produces a version of your program for Algorand and a version of your program for Ethereum. And of course, in the future, it will create versions for many other blockchains. And each one of those has different consensus networks, right? That's what it means. So because they have different consensus networks, that means the middleware has to behave differently to talk to the smart contract. And so what's happening right here is that we're not actually loading the standard library, we're loading something that can load the standard library in the future, based on which standard library we decide to use. And when I say decide to use, which actual blockchain we decide to deploy on. I'll show you in a little bit when we run the program how we can select which blockchain we want to use. So similarly, each blockchain has a different notion of what the real currency of the chain is. So for example, on Ethereum, people know about an ETH, but an ETH actually isn't what you transact in. You really transact in what's called a WEI. That's a WEI. And I think that a WEI is like 2 to the negative 18th of a single ETH. And similarly on Algorand, you don't actually use algos, you use microalgos, which are like 2 to the negative 6 algos. And so what we're saying right here when we say parse currency, we're saying take the number 10 and treat that as whatever people normally mean when they talk about currencies on this, and then turn that into what the real currency of that network is. So in this case, that would turn 10 ETH into 10 to the 8, 10 to the 19 WEI, or 10 algos into 10 to the 7 microalgos. Okay, so the next thing we're going to do is we're going to make accounts, and I like to name my account ACC Alice so I can remember who it is and what it is. You can name it whatever you want. There's this style of variable naming that people call Hungarian notation, which is where you encode the type of your program, the type of the value into the variable name. And I grew up writing code using Hungarian notation, and kind of stuck in me, and I can't unsee it. So anyway, so we're going to make account Alice, where we're going to do new test account that has the starting balance. And then we'll make another account for Bob, where we'll make a new test account with the starting balance. Then, once we have those two accounts, then what we're going to do is we're going to actually deploy the smart contract. So remember that Reach has made the smart contract behind the scenes. Every dApp has a smart contract. Maybe a dApp has multiple smart contracts, but definitely has one. And because we're on the user's computer and we have to, get the smart contract running, that means that we have to take it from the user's computer and put it on the consensus network. That process is called deploying. So we'll just sort of decide that Alice is the one that deploys it. So we'll say that Alice is going to deploy. And now what does she deploy? She'll deploy the backend. Now remember, the backend is what we named the import of the compiled version of the Reach program. And deploy, if you're searching for a synonym for that, it would be like launch or serve or host. Those would all be pretty decent analogies for deploy. Kind of the only difference, though, is that if I were to say serve, that kind of makes it sound like the user's computer is the one that's serving it, or the user is the one that's serving it, but really it's the user who's taking responsibility for putting it on the consensus network. And once they put it on the consensus network, then it exists independent of all of the of any particular user. It's now just run by everybody simultaneously. This is kind of the thing that is special about consensus networks, that they enable this abstraction of the universal computer run by everybody in the world to work together. Yeah. Okay, so Alice will actually deploy it, and then we'll have Bob who will attach to it. And he doesn't attach to just any contract. You know what I mean? It's not like he attaches with no arguments right here. He needs to know what Reach program he's attaching to. So we need to say, this is the program that you're attaching to, this backend. And we also need to know where it was actually deployed. And so we'll write contract Alice get info. And
Can everybody mute, please?
Calling get info there will return information about where Alice launched it. So because Alice takes it from her computer and puts it on the consensus network, it has to be somewhere, So it has an address on Ethereum. On Algorand, it kind of has a combination of an address and what's called an application ID. So this get info stores information that someone else would need to be able to contact this particular contract. And so what Bob says is he says, I'm going to attach to this Reach program, and it's located here. And this attaching function is going to actually go check and make sure that what's there really is this program. So it'll verify. This is called contract verification. It'll check that the program on the chain, on the consensus network, is the one that you think it is. Okay, so at this point, what we've done is we've loaded the standard library. We've created test accounts for Alice and Bob. We've had Alice deploy the program, and then we've had Bob attach to that program. Now, of course, we need to actually run the backend. Now, remember that we specified that we wanted this role to be named Alice and this role to be named Bob. So inside of this backend object that got compiled, there's a function named Alice and there's a function named Bob. So you might think that what we would do is we would write backend.alice, and then we would call it with some information, and we would do backend.bob, and we'd call it with some information. And that's basically what we're going to do, except that we want Alice and Bob to run simultaneously. And that's because this is a test program that's going to basically be both sides of the program so that we can see what happens. Of course, in the real deployment, any particular user will only be either Alice or Bob, but we're going to be both in this test program. And now, because we want these programs to run at the same time, we can't say, well, run Alice, and then when you're done, run Bob. We basically need to start new threads of computation. And in JavaScript, the way that you represent threads is by these promise objects that I mentioned before. So we do that by, these in fact will return promises. And after they return those promises, what we need to do is wait for both of those promises to be done. And once both of them are done, now the entire program is done. So we can do that by writing await promise.all. Then this is a function we're calling, and you give it an array of promises. And so what we're doing right here is we're saying, look at this array of promises. Go look at all of them. and then take all of those and turn that into one big promise. And that one big promise is done when all of those are done, and let's wait for that one to be done. Now, what information do we have to give Alice? Well, notice that right here it's backend.alice, so that's the compiled version of Alice. That's like the part of this program that corresponds to what A does. In other words, it's actually totally disconnected from this representation of the contract and from this account. So we have to explicitly tell that backend to use this particular representation of the contract, the one that the Alice account deployed. And we also have to pass in an object right here, this object. And this object corresponds to that object. This object in the JavaScript program is this object in the Reach program. And what is that thing? What that object is the interface between the front end and the middleware. It's the way for the middleware. It's really the arrow backwards. So there's an arrow that goes from the front end to the middleware. That's backend.alice. And then there's an arrow that goes back the other direction from the middleware to the front end. That's this object right here. Okay, so we'll say run the Alice version of this program and run it with Alice, with the Alice representation of the contract. And then we'll do the kind of the same thing with Bob, where we'll say run attaching to the Bob instance, run with this backend interface, and then we're good to go. Okay, so that was kind of a very long way to explain writing 24 lines of code, but now we really have every single piece under our belt. So now what we'll do is we'll run this program. So we have our MJS file, which is our front end. We have our Reach program. We actually already compiled our Reach program. That's in the build directory. Now, how do we actually run this? So how do you run node programs? How do I run a node program? This is too complicated for me. There's more steps. I don't want to do this. Okay. So what Reach does is it encapsulates all of the details about running one of your node programs, including running a devnet for your chosen consensus network. It just encapsulates that all into a function that we call reach run. So you run reach run, and what it is going to do, I'm going to just wait a little bit to explain what's going to happen before we see it happen. It is going to make sure your program is compiled. Then it is going to start up a devnet for your chosen consensus network. Then it's going to run your program, your front end right there, and we're going to see what happens. And then it's going to stop and it will close those things down. And how is it going to run your devnet? It's going to run it using Docker. That's why we made sure that we had Docker installed earlier, because it's going to start up a virtual machine that is an instance of your chosen consensus network. How's it going to run your program? Well, you don't have Node installed. What it's going to do is it's going to run that inside of another Docker virtual machine. And it's going to connect those two Docker virtual machines together so they can talk to one another. Okay, so when we run reach run, like I said, it goes and makes sure it's compiled. Now it builds a little custom Docker image with your program in it. It goes off and it starts a devnet for the tutorial. It starts a network to connect them together. It then runs your program, and then your program ran between this line right here. So see, it says that the module loader is experimental. Remember how we used node modules? There's been experimental for the last 15 years or something like that. And then we're done. So because our program didn't actually do anything. Well, I mean, it did something, but we didn't see anything happen because, there were no messages that got printed out or anything like that. If you, if you're the kind of person that wants your computer to start up and not show a picture, but instead show black text with lots of stuff being printed out to really know that something's happening. I remember, I mentioned, first installing Linux a long time ago from a CD that I got in a speakeasy. Back then, you tried super, super hard to figure out a way to get your Linux computer to show a picture when it was loading. Nowadays, that's easy. So instead, the cool kids, you want to see, white text on black. So anyways, we can get Reach to print out a bunch of junk if you want by writing reach debug, yes, and then we can run, and now it's going to print out lots of stuff. So it prints out stuff like, you know, well, there's a lot of stuff. It's going to go and it's going to make sure that it can connect to your DevNet. And then it's going to create an account, and then it's going to send funds to that account. And then here's the transfer, in case you wanted to know all the gory bits. And then it's going to run the reach program. Where is that? Down here in the guts somewhere. Where is it? Here we go. So here we're deploying the program, we're making a contract factory, we're deploying it, and then we're done. It's over. Because this program, our reach program actually doesn't do anything. You know what I mean? It just exists and then it's over. So nothing really happens to this program. It just runs and then it's immediately over. So anyways, so that's what we did. Now notice that when I ran the program this way, it ran it on Ethereum. And that's just because the default network is Ethereum. If we run reach connector mode equals algo, then now it's going to run it on Algorand. And Algorand has to start a few more things. It's got to start a Postgres database, because there's something called an indexer in Algorand that uses a database. Then it starts the Algorand DevNet, and then now the program's running. And that Ethereum program, it finished instantly, because Ethereum has what is called a dev node. And a dev node is an instance of the network that basically sits there waiting for a developer to send it a transaction, and then it immediately does what that transaction needs to do, and then it goes and it just waits for the next one. Algorand doesn't have a dev node yet, and so what we just did is we ran the program at the same speed it would happen in the real world. If we were to have run the Ethereum program at the real way that it would happen in the real world, not only would we have just spent $330 or something like that because we just launched it 3 times, we would also have spent 45 minutes doing all this, because it takes a really long time for Ethereum transactions to complete. So anyways, at least when you test on Algorand, you'll know that you're getting the behavior of the real network. But because that lack of a dev node, and Algorand is working on building a dev node so that we can speed up this kind of development. Because of that, it tends to be convenient to test on Ethereum, and then move to Algorand when you're ready to go. Similarly, you can run in reach connector mode and with debugging on when you run on Algorand, and way more stuff is going to print out, because there's actually more steps involved when you do things on Algorand. Because when you launch a contract, basically there's more stuff behind the scenes when you launch a contract. But anyway, so that's happening right now. Okay, so we've now completed this step of the tutorial, 2.2. And I believe that we're going to 2.3 tonight. So let's just close that off. Go back to here, our 2 programs. Okay, so on the top, we've got our reach program. On the bottom, we've got our front-end program. Now, what is our program going to do tonight? So, if you have tried to learn about dApp development before, you have to typically learn some complicated domain. And what do I mean by a domain? A domain is like what a program does. So for instance, I could write a program for my phone, that is like a photo sharing app. Or I could write a program for my phone that is like a language learning program. So those are the domains, language learning or photo sharing. And, the actual technology I'm using is mobile app development. And you can learn mobile app development and know nothing about photo sharing and know nothing about language learning, even though those are actually 2 extremely popular kinds of mobile apps to build. Similarly, you could learn dApps by learning a domain like a market maker or a DAO or a DEX. These are extremely popular domains to choose to write dApps for. In my opinion, those domains are very exciting, but they're advanced. That would be like teaching someone mobile app development, and the program that you first give them to build would be something like, I don't know, like Siri. So Siri is a really cool mobile app where it, takes in your voice data and decodes it and, runs a machine learning model and takes that machine learning model and figures out what you want and then uses that to try to answer the question and then brings it back to you and does sound synthesis. Like, that's a really cool program. And someone who likes mobile apps, maybe that's the program that they want to build. And maybe you want to build a DEX or a market maker or something like that. But if you walk up to dApp development and you have to learn one of those domains first, then there's this very big hurdle in front of you where you have to master not only the domain, but also the technology. And what we've decided to do with the Reach documentation is we're going to teach you dApp development by using a boring domain that you probably already know about. This is sort of the equivalent of, like the flashlight app on your phone or something like this. It's kind of useful. There's definitely an argument for why you would want to have a flashlight phone on your app, and the program that we're going to write, it does something. But, there are no multi-billion dollar businesses built around our domain for this program, but it has the advantage of it's very easy to define, and you probably all already know what it is. And so what we've decided to do is have the domain of the tutorial be a game of rock, paper, scissors. So rock, paper, scissors is the game that you play, when there's a tie in some other game, or when you want to decide who will go first, where two people simultaneously choose hands, and these hands are either scissors or rock or paper. And so two people simultaneously, unbeknownst to the other one, see my two hands are the two players, so they both decide what they're going to do separately, and then at the same time they show what they've chosen, and then we have rules to determine who won. And so the rules are that scissors cuts paper, paper covers rock, and rock smashes scissors. And so that's the entire rules of the game of rock, paper, scissors. It's also called Rochambeau. Sometimes in other countries they will have different names for these things, but it's a pretty common game in the human experience. Maybe a little bit Western. The particular name's rock, paper, scissors. So that's the game that we're gonna encode as a dApp. And we're going to make it a dApp by making it so that there is a wager over the result of the game. So Alice is going to propose a game of rock, paper, scissors, where the winner will receive some number of network tokens, like algos or Ethereum or something like that. And then the two players will simultaneously share their hands. And then after they simultaneously share their hands, the winner will receive the proceeds, the two wagers put together. And if there's a tie, then they'll both get their wagers back. So that's what our program's going to be. Now, inside of the Reach program, we need to make a decision about where the front end begins, really where the front end stops and the middleware begins. Because remember, Reach produces these two things. So maybe I'll add another row to this picture right here, where I'll say, Reach makes these, programmer does this. I shall write you do this. Reach makes these, you do this, and then we'll say Gma is this. So your Gma is the user, and you write the front end, and then Reach makes the middleware and the smart contract. So you need to decide what you're going to program in JavaScript, or whatever your front-end language is. One of the advanced sections of the tutorial tells you how to make this part of your program in other languages like Python and Go and stuff like that. So anyways, so you have to decide what part the front end is going to be responsible for and what part the middleware is going to be responsible for. So the middleware is the one who's ultimately going to share the hand that you choose, and it's going to share it with the other side. But it needs to know like what hand to even decide. Now, one way that you could imagine doing this is that like you could program it so that the middleware always chooses a random hand, because there's an argument to be made that that is an optimal strategy. It's not really an optimal strategy, though, because if you know that your opponent is a wimpy human, then they might try to, they might have a plan for how they're going to play rock, paper, scissors, and if you think you know that plan, then you can counter them better than playing randomly. So what we're going to do is we're going to say that Alice and Bob, they both are going to put responsibility for choosing the hand onto the front end. And the way that they'll do that is that we're going to replace this object right here. Remember, that object is the interface between the middleware and the front end. And that object, of course, corresponds to this object in the JavaScript program. We're going to put the responsibility in there. So we're going to make it so that object is called player. And let's go define player. So player is going to be an object that has a getHand function. And this getHand function takes in nothing. Its domain is empty. And it will return a number. uint stands for unsigned integer. And then it will also have a function called coutcome that will take a number, and then it will return nothing. And so right here we're writing the domain, right here we're writing the range. And now these two functions right here have to be implemented in our JavaScript. We'll see that in a moment. Actually, I guess we'll see it right now. So let's write it. Let's write those functions. So let's go down here and we'll write player, and we'll say Alice. And then down here we'll write player, and we'll write Bob. And then I'm going to write a function in JavaScript that is going to be called player. It will be parameterized over who the player is. And what it's going to do is it is going to return an object with these functions. So it'll have a getHand function, and it'll have a coutcome function. This is my micro break that makes sure that I don't type too long without hurting my wrists. This is the time for the PSA. Programmers, your wrists are your most valuable asset. You got to take care of them. Make sure that you stretch your wrists regularly. You take breaks. You get up and pay attention to your back. All right. We have to have a coutcome function, and the coutcome will get a outcome variable. Okay. Now, inside the getHand function, we've got to return the hand. Okay, so we've got to write these functions. What I'm going to do for testing purposes is my getHand function will just choose a hand randomly. So randomly generates a number between 0 and 1. And then what I'm going to do is I'm going to multiply that by 3. So now it's a number between 0 and 2. It's either 0, 1, or 2. ... dots, a whole bunch of things. And then we'll floor that. And by flooring that, now it's either 0, 1, or 2. And so we'll represent in our program rock as 0, paper as 1, and scissors as 2. And then let's print out, we'll say console log, and we'll say who played, and then we'll print out what the hand is. So we'll make a little variable right here, hand that has rock, paper, and scissors. Because as I said, 0 is rock, 1 is paper, 2 is scissors. And we'll make another variable called outcome, which is going to be Bob wins, a draw, and then Alice wins. And then when we see the outcome, we'll print out that this person who saw the outcome, and then we'll print out what the outcome is, because the outcome is represented as a number, just like the hand is represented as a number. Okay, there we go. Now, let's go back to the Reach program. So in the Reach program, we've now got to actually write the part of the DApp that is going to do something. So essentially what we're going to have this program do is we're going to say Alice will pick her hand, and share it. Then we'll have Bob pick his hand and share it. And then we'll compute who won. Compute who won. All right, now how do we do this? So as I mentioned before, this A variable in the program is the reach representation of Alice. And so in between these braces right here, which is our actual program, you can kind of think of it as a script. Now, when I say a script, I mean like a script for a play, or another way to think about it is the rules of a game, like chess or whatever. And so we'll say that in the first step, Alice is going to do something, and we write that as Alice only. So Alice only means this right here, I'm about to write something that only Alice does. And we're going to write a block of code. And the only way to write a block of code in JavaScript is by writing a function. And so we're going to write a function that takes no arguments, and then inside here, this function will be called only by Alice. And what she'll do is she will call her interact function and get her hand. So interact right here is the name that Reach gives to this object right here. This object that we've called player, that has these functions, get hand and see outcome, it appears inside of the Reach program with the special name interact. And you can only use interact when you're inside of one of these onlys. And so what this means is that the compiled version of this program, backend.alice, it is going to call this function as interact. So this value right here, that is interact. And so it will literally call this function right here, get hand. And when it calls that, we'll see it print out Alice played rock or paper or whatever, and then it will get returned. And then that value right there that gets returned is now named hand A inside of the Reach program. Then what we're going to do is we're going to write A is going to publish hand A. This is the next kind of really big idea of Reach. Let's go back up to our picture. Remember that smart contracts, they run on the consensus network. And the consensus network is this worldwide computation that's being run, where everyone can go look and see what is happening to all of those programs. We can actually do this right now. So let's go to Etherscan. Okay. So Etherscan, so just now, just 1 minute and 11 seconds ago, right here, these transactions got called. And look, this function right here was called. Where's a contract call? Yeah. So right here, this is a USD coin from Binance to there. So there was a transfer. So we can go look, and we can see that this contract right here, A0B86991, that contract just got called with a particular function. What function did it get called with? I think we can click and we can see more. So look, it got called with this data. This data right here is what was just published. We got the method identifier, that, and then the first argument, the address was this one. So it's 0CA91D. That's why Etherscan prints out 0C91D right there. And then the second one, which was the value, is 9EEE6E22. What is that? That is this number right here. So this number right here, this withdraw, that number is this number. So every single time anything happens on the consensus network, it is public information that is shared with the entire world. And that's why in a Reach program, we use the word publish to refer to what happens when A wants to share information with the DApp. Because, of course, Alice, she doesn't want to share information with the consensus network. She doesn't want to share information with the smart contract. She wants to share information with Bob, right? But she wants to share information with Bob under the constraint that everyone is following the rules. And that's what smart contracts are for. What smart contracts are for is they are to guarantee that everyone who is trying to share information is following the same rules when they do so. Now, the way that we've written this program so far, there's actually no constraints on what Alice is allowed to share. And when you write a Reach program, you explicitly write down the constraints on what Alice is allowed to share in between the publish and the commit line. So in between these two lines right here, we constrain what Alice is allowed to share. But we don't have any constraints like that right now, so we don't actually say anything. And this is the job of the smart contract. The job of the smart contract is to make sure that these things right here that get shared with the whole world are valid. Now, in the case of, this example program that we just sort of spied on, what it did, if we looked behind the scenes, is it made sure that this account right here really actually had this much USDC. So if we were to look in its version of a reach program, it would have a publish that would say who's it coming, who's the value being transferred from, and what is the value. And then in between that publish and the commit, it would say, let's make sure that that address really has this number in it. And that's what would be inside of that the USDC program. Okay, so that's what Alice does. Now, the next thing that we need to do is do something almost identical for Bob. Because Bob, he is going to share. He's going to compute what his hand is, interact.getHand. And we'll do this. And then we'll have B, publish hand B. And then now we actually do want to compute some, we actually do want to do something, which is that we want to check to figure out who the winner is. We'll say that the outcome is going to be hand A plus 4 minus hand B percent 3. Now, that's a bunch of fancy math that turns out to compute who the winner of a game of rock, paper, scissors is. If you want to see behind the curtains for why this works, when you do modulo 3, think of that as like a clock. Okay, so when you do modular arithmetic, you're doing a clock. We're going to skip this one. I did tell you that you got to monitor your hands, but maybe we'll wait to skip it until I finish explaining this modular arithmetic thing. So modular arithmetic is math on a clock. So when you say that 5 hours after 8 o'clock is 1 in the afternoon, that's because 8 plus 5 modulo 12 is 1. So anyways, when you're thinking about rock, paper, scissors, there are only 3 options: rock, paper, and scissors. And by choosing them in that order, rock is beaten by paper, paper is beaten by scissors, scissors is beaten by rock. So if you lay them out in that order, each one is beaten by the next one in the order. So how does this work? So if we take hand A, suppose that's rock, and then suppose hand B were paper, then we do 4 minus paper. So paper is 1, so 4 minus 1 is 3. So now we have 3, which would be over here, which is 1. Okay, so 1 is the thing that it beats. And so if we add those two together, then we will get 2, which we modulo 3, and then that leaves it where it is. The modulo is just to make sure that we wrap around. Okay, now why do we wrap around there? By wrapping around there, we now get the outcomes, where the outcomes are Bob wins, then draw, and then Alice. So whenever we do that operation and we end up with 0, that means that Bob won. The second value was the right one. And if we ever get back 2, that means that Alice won. So anyways, you can check. We'll check later automatically, using the verification that this is right, but you can check this for yourself. So now we'll commit, and then we're good to go. But actually, one last thing is that we want to actually see the outcome. And so we will finally do, what we could do is we could say A only, and then inside here we could write interact.see outcome, and then we could write the exact same thing for Bob, but copying code is ugly. Sometimes you just want to do the same thing for both parts of a program. And so Reach has this feature that's called each, where you can say, let's have each one in this array do the same thing. So A will do this, and then B will do this. All right. So at this point, we can now try to run our program. So let's go run the program. And unfortunately, I put a semicolon in the wrong spot. So on line 23, which was right here, I had a semicolon, but I meant to have a comma. That's what I get for not using the IDE. Okay, now we got another error, which says on line 37 right here, this one, inside of this only, it says invalid binding in only hand A. Secret identifiers must be prefixed by underscore. Did you mean to declassify? This is kind of another important idea about Reach programs. We assume that all values that come from the front end, remember the front end is the thing that you write that your user interacts with, we assume that all of those things are secret and you don't want to share them. You don't want to automatically expose them without the user's permission, or rather without explicitly deciding that you want that. And so what reach does is it basically makes it so that anything that comes from an interact function is sort of like contaminated, and it can never be allowed to flow to a publish unless you explicitly declassify it. So we'll write declassify right here, and we'll have to do the same thing down here. Declassify. The code actually said that, see, it says declassify right here. And by the way, anytime you're looking at reach programs and you see a word like declassify, you can, click on it and we'll explain what it means. So declassify, the declassify primitive performs a declassification of the given argument. Sometimes there's very circuitous things. So what's a declassification? We can click on this and we can say, all local state is initially private until it is explicitly made public via a declassification, which is a kind of local computation. So many links will end you up at this page that describes kind of the model of reach programs. This picture can be useful where values start off as local and private, then they are declassified and become local and public, and then they get published, and then they are available to the entire consensus, i.e. the entire world. Okay, so now that we've fixed the declassify problem, now we can run the program and see what happens. So now we run the program, and Alice played paper, Bob played paper, Alice saw that the outcome was a draw, and Bob saw the outcome was a draw. If we run the program again, we'll probably get different values. Nope, we got paper. Both got paper. I wonder why we keep getting paper. Now we got scissors and rock. So Bob won that time because rock smashes scissors. Let's run again. See if we can get a different value. Now we got rock and scissors. So Alice won that time. Let's run again. This is very exciting. Now we got two papers again. So anyways, so as you can see, our program is doing stuff. Now, this program right here, the reach program is 58 lines, plus I got my picture at the top. Okay, so it's not really 58 lines. And then we got our JavaScript program, which down here is 37 lines. And you may wonder what happened behind the scenes. You know what I mean? What really got compiled? Because remember, our reach program, it contains simultaneously the middleware and the smart contract. So as we saw before, we can go check out that file if we want. Okay, so this is the file that got generated. And so here is the Alice code. And, this code is not designed for public consumption, but it has in it everything that's going on here. So the first thing that Alice does is she's going to publish a value. Then she's going to read a value from Bob, and then she's going to read the outcome value, and then it will go to see outcome. Okay, so we can see all of those things happen inside of the program. So see, it starts off by calling interact get hand. And notice that we have some extra information here. Let's just sort of pause real fast. What is this extra information? Reach checks to make sure that your front end isn't breaking rules. So let's just make it so that our program is bad, and rather than returning a number, it returns true. So what's going to happen when we try to run this program? If we try to run the program, we're going to get an error, and it says that I expected a big number, a number, or a string, but I got true. And it says protect failed, expected a uend, but got true at line 38 in the reach program. Line 38 in the reach program is this line right here. And it was inside of line 37, which is this, and 37, which is that. It was on a call to get hand from Alice. So we can actually see a mistake in the front end gets caught automatically by the middle layer, which checks to make sure the front end is not making mistakes. So we can do that. Okay, so anyways, so we get the hand, and then what we're going to do is we're going to send that hand. This is right here, says send receive. So it's going to send the hand. And then what it's going to do is it's going to receive the other hand. And then what it's going to do is it's going to perform the operation to compute the outcome, which is right here, where we do a modulo, an add, a subtract. That's that computation in our program right there. It's computation. And then it will call see outcome with that value, and then that will make it so that Alice can get to actually see what the outcome is. And Bob has a corresponding part of the program where we go through and we just do the opposite. He receives the value and then gets his hand, and then receives the next value, and then sends his value, and then produces the outcome, and then shows the outcome. And notice that they both compute the outcome on their own. And the reason that they do it on their own is because they don't actually need the smart contract to do that, because they have all agreed on what the two hands are. So because they know what the two hands are, because they've been published and verified by the consensus network, they can now compute them individually. One of the things that Reach does is it basically figures out the optimal way to remove stuff from the smart contract and put them on the individual middleware layers, because basically running things in the smart contract is expensive. You've probably heard of gas. So because it's expensive to run things on the smart contract, we want to do as little as possible there. And so what Reach will do is it will basically produce the maximal separation between the two programs. So anyways, so that is the the program. We can run it. As I mentioned, this test example runs on Ethereum, but we can just tell it to go run on Algorand if we want.